Another topic we covered in the context of measures of association has to do with shifting and rescaling data. A limitation of covariance and correlation is that they are only useful and only apply to linear relationships. So one way to think about working with data, especially numerical data, is how we can shift and transform our data. So the most very basic transformation is what we call a linear transformation. This is shifting and rescaling a set of data. So the original data is this x variable. When we multiply it by some fixed value, by some constant b, and we add a constant a, right, where a can be negative or positive, what we're doing is we're conducting a linear transformation. What we're doing is we're shifting the data by a, right, we're recentering it, and we're changing the scale by b. Right? This is called shifting and rescaling. Linear transformations are very common. Right? They change the center and spread of the data. So we change the center by adding a, and we change the spread by multiplying by b. But the nice thing about a linear transformation is it doesn't fundamentally change the shape of the distribution for the set of numerical observations. Right? It's not going to change the shape, but it's going to change where the center lies and the spread of the data. We see linear transformations all the time, and a lot of statistics will use linear transformations such as this. Just to be clear, what a linear transformation does is it takes the raw data of x, you multiply by b, that will change the scale or spread, and you add a. And by adding a, you will shift around the center of the data. And then you have a new variable y, which is the variable x, but which has been linearly transformed. Lots of linear transformations, but the most common by far is what we call a z-score or a standard score. Right? This is a common way in which we write a z-score. What you do is you take the original data, x, you subtract out the mean, which we call x bar, and you divide by the standard deviation. Right? After subtracting out the mean, our new mean is now 0. And then by dividing by s, our variance or standard deviation is now 1. This resulting variable is a z-score. The z-score has the same shape as the original variable x, but the mean is now 0 instead of x bar, and the variance is now 1 instead of s squared. Or in a related fashion, the standard deviation is now 1 instead of s. The z-score is very useful because we can take different variables and put them on the same metric, on the same distribution. And the z-score has a very clear interpretation. Right? It's a standardized score, meaning it's standardized, in the sense you have a mean of 0 and a spread of 1, a variance of 1, or similarly a standard deviation of 1. And the z-score itself can be interpreted as the number of standard deviations. The raw score deviates from the mean, how far away it is from the mean. Okay. Besides linear transformations, such as the z-score, we also have nonlinear transformations of data. There are various nonlinear transformations of data. So in these examples, the raw data is x, and our output is y. So y's are non-linearly transformed data. So you can take the square root of x, you can take the log of x, you can take 1 over x. Lots of different ways to construct nonlinear transformations. But the basic idea with a nonlinear transformation is you take some set of data and you change the shape of the distribution. Now, why would you want to change the shape of the distribution? Well, usually we do it so that we can make the data distribution more symmetric. We want to reduce outliers, or we want to reduce skewness. This is very useful for when we want to use measures of association and statistical models that require the assumption of linearity. So covariance and correlation require the assumption of a linear relationship between x and y. Covariance and correlation only capture the linear relationship between x and y. So what we can do sometimes is non-linearly transform our data, that is, reduce the presence of outliers or reduce skewness, so that a nonlinear relationship appears as linear. So it is linear after we transform the data. So instead of a correlation between x and y, we might run a correlation between x and a transformed version of y, a logged version of y, thereby making it that the relationship between the two are linear after this transformation. So we use nonlinear transformations on data so that the assumptions of linearity can hold when we run models such as linear regression and for measures of association such as covariance and correlation. To recap, transformation of data really involves two major kinds of transformations. Linear transformation, the most common of which is the z-score, and then a nonlinear transformation in which we might log a variable, apply a logarithmic transformation, or we might square a variable. And with that, we cover the basics of transforming data for statistical analyses.